All right, today we're going to talk about elementary matrices. So the goal today is to have a new method of calculating determinant. And in particular, by row reducing. So remember that one of the key reasons we care about the determinant is that if the determinant is not 0, then that's the same thing. That's equivalent to that our matrix is invertible, which is the same thing as the columns of A are linearly independent. And this is the same thing as A reduces to the identity matrix. So what we really want to be able to do is ordinarily, if we want to check if A is invertible or if the columns of A are linearly independent, what we would do is we would row reduce the matrix and see if we got the identity. We would take this line right here and say, okay, they're independent if it reduces to the identity matrix, or it's invertible if it reduces the identity matrix. And now what we want to be able to do is in the same sense, what we want to be able to do is to calculate the determinant just by row reducing. And the medium for doing this is going to be elementary matrices. All right, so that begs the question, what is an elementary matrix? So an elementary matrix in some sense is or strongly encodes a row operation. So we're going to go through our 3 favorite row operations. And every time you do one of those, you're really multiplying by a very specific matrix. So let's just go through them. So the first one we have is if we take a matrix, and if we multiply a certain row by a scalar, in this case, we'll say k, right? Then we'll get our result. In this case, row 1 is multiplied by k. But it turns out this is the same thing as multiplying by the identity matrix, except for a k for that given row. So here we're changing the first row. We're multiplying it by k. So there's going to be a k in that row for our elementary matrix. And otherwise, it's just going to be just like the identity. And if we multiply this out, sure enough, we're going to get the same thing. So scaling by a row is really just multiplying by the identity matrix with one of those ones replaced with the scalar in just the right row. All right, we have the next one. So the next one is the other row operation we use a lot, which is we're going to take one row. So in this case, we may take row 2 and add some multiple of another row. And so this is something we know and love to do. Like that. And as it turns out, that's the same thing as multiplying by a certain specific elementary matrix. It's going to be the identity matrix again, except instead of the k being on the diagonal, that k is going to be in the specific position. It's going to be in the row corresponding to the row you're changing, and the column is going to correspond to the row that you're adding, the row that you're adding to it. So if we do this, we can check that we're going to get the same thing. So for example, we can check those two will give us that one. So the second row, first column certainly matches up with what we wanted. So you can check the rest. So that means that our 2 favorite row operations correspond to these nice simple matrices. And indeed, just to emphasize again, these elementary row operations are really near identity matrices. right? So they're just the identity matrix with one small tweak to them. And we have one additional elementary matrix that we seldom use, one additional row operation. And that is if we want to swap two rows. So sometimes we might want to swap two rows. And we're going to get that by taking the identity matrix and swapping the two positions. So instead of writing the identity matrix as normal, you're going to take the two rows you want and you're going to swap them. So here we moved the 1 off the main diagonal. Kind of swap them up. And if we multiply this by A, B, C, D, we can check that we'll certainly end up with the same thing. So for example, in the second row in the first column, we'll end up with A. All right, so that's all nice and dandy, but what makes these elementary matrices so great is that we know the determinants of these elementary matrices. So we have these 3 ones that we have. We have scaling a row like this, and in general, it's going to look like ones on the diagonal. So if it's a bigger matrix, elementary matrices are not limited to 2 by 2s. They're the size of whatever matrix you're dealing with, but it's going to have a K in the row that you're scaling instead of a 1 for the identity matrix. So the scale's a row. And what's really nice is that it's very clear what the determinant of this matrix is. So based on the general formula, there's only one pattern that's allowed. It's a diagonal matrix. So we know that the determinant of this matrix is just equal to the product of the diagonal, which in this case is just going to give you K. And so now we can go to the next one. This one it's the same thing as the identity matrix, except you might have a K off the diagonal. Everything else is 0. And here, this K right here corresponds to multiplying a multiple of some other row to that one. So in this particular case, we're going to be, that's the third row, but it's the second column. So we're multiplying K times the second row and adding it to the third column. And again, what's really nice here is we can calculate the determinant. There's exactly one pattern which corresponds to the diagonal. So in this case, the determinant of this matrix is just 1. And then likewise, we go through our last one, which we seldom use, but that's the swapping. This one's a little less clear what the determinant's going to be. So whatever rows you swap, you're going to swap their positions like that. Everything else is just going to be 0. So these are the ones that get swapped right here. So this would correspond to row 3 swapping with row 4. And just like what we did last time, we looked at the pattern. There's still only one pattern that's allowed, but now one of them is going to be negative. So there's one negatively oriented pair. So the determinant of this guy is going to be -1. All right, so why is this useful? Well, it turns out that every matrix you can construct using row operations as some product of elementary matrices. So let's just do an example that we already know and love to do. We're going to calculate the inverse of a nice, easy matrix. And then we're going to go back and use these facts to calculate the determinant of that matrix. So let's do an example. And this is going to showcase many things about elementary matrices. So what we're going to do is we're going to look at this matrix. We're going to look at 2, 4, 4, 2. And the question we want to answer is what's the determinant? But what we're going to do is first we're going to calculate the inverse. And then we're going to showcase all the things we can do with the information we get by row reducing this matrix. And this is a nice 2x2. It's going to be very fast. So this should be a very digestible example, but there's no reason we can't take these ideas and extend them to larger matrices. So just keep that in mind. All right, so what we're going to do is we're going to calculate the inverse. All right, and we do this by row reducing. So we're going to row reduce this matrix. We don't actually need to calculate the inverse per se, but let's just calculate the inverse in the way that we know how to do it. But the key thing is we're going to row reduce this matrix step by step. And we're going to keep very careful track of this step. So also keep in mind that what we're doing when we're really doing this inverse is this is really AX, where X is a matrix, equals the identity. So we're solving, right? When we use this kind of technique, this mechanic, right? What we're really doing is this line right here is really just a placeholder for X equals, and we're solving for X by performing operations on both sides of this equation. And those operations are really multiplying both sides by some elementary matrix. All right, so let's go with it. So here we have that one. So we're going to take row 1 and we're going to scale that by a factor of 2. And then we're going to go ahead and take row 2 and subtract 4 times row 1. Then we're going to scale this row, that second row, by -6 by dividing it by -6, or 1/6. That's a 2, row 2. And then finally, we're going to go ahead and zero that corner out by taking row 1 and subtracting twice row 2. So there we go. We have the inverse. So this is our inverse right here. Cool. All right, but I want to point out that we can actually now construct the inverse. So what really happened here? So we're going to go back and we're going to use, instead of doing this with row operations, we're going to look at it like matrix algebra. And I want to point out that at every step along the way, what we really did is we multiplied both sides by some elementary row, some elementary matrix, which corresponds to exactly what we did with the row operations. So for example, this first step, what we really did is we multiplied both sides here on both sides by the matrix 1/2, 0, 0, 1. And there's an X there. Let's make sure that's there. There's an X. And then the next step is, what do we do on the next step? We multiply both sides by yet another matrix. So the matrix we multiply both sides on is this one. And then the next one we multiplied by was scaling 1/6. So we're going to put a 1/6 in the second row. All right, and then finally, we multiplied by another row operation matrix on both sides. And so now we have all these matrices right here. Now this may seem like a mess, but we know what's on the right now. On the right, this right here is A inverse. That's what we got. We multiplied by A inverse. And so this whole equation really here, right? This, when you do this row operation, why does this trick work? Well, it works because this is just A inverse times A. Those cancel, and we get the X equals A inverse. So X is equal to whatever's here on the right, and lo and behold, there's A inverse. What's also really cool, so this equation right here, we can then boil this equation down. What does this mean? This means that our X, which is equal to A inverse, is equal to the product of all of these elementary operations. All right, so far we haven't talked about determinants, but it's coming, it's coming. All right, so A inverse is equal to all those. So now when we do this, we know the determinant of A inverse is equal to the determinant of all these guys all together. And we know that the determinant can be broken up matrix by matrix. So this is equal to the determinant of the first matrix times the determinant of the second one times the determinant of the third one times the determinant of the last one. And so what we can do is we now know the determinant of A inverse. We now know the determinant of those individual 2x2s because they're just elementary row operations. And we know that they have very nice and easy determinants. So these determinants, this is going to give us 1 times minus a sixth times 1 times 1/2. So A inverse, the determinant of A inverse, is just going to be minus 1/12. And based on the rules of determinants, we know that this means the determinant of A is equal to minus 12. So we can use the elementary matrices to figure out the determinant. Now that's a lot of work. So part of the reason I'm doing this is to show you a lot of things. One is that you can break down every matrix into a product of elementary matrices, but also to show you why this works. And now what we're going to do is we're going to shortcut this process a lot more. We're going to go back and kind of figure out where do the numbers come from? Where do the 1 and the minus 1/6 and the 1/2, so where do all those numbers come from? So you don't have to necessarily write out the elementary matrices every time, but you should at least acknowledge when you're using the method, every time you're doing row operations to find an inverse, you're really just applying, instead of dividing both sides of an equation by 2 or dividing or multiplying both sides by 5, you're really multiplying both sides by some elementary matrix every time you do a row operation. All right, so let's go back and figure out where this 1 came from. So this 1 came from the fact that now keep in mind, matrices are applied right to left. So this 1 here is actually the last step we did, and that was one of these add a row to another row. So this contributed a factor of 1 to our determinant. Where did this -6 come from? This -6 came from the fact that we scaled the row. That's our multiplied by -1/6. This -1 came from the fact that we did another add a row to another row. And then finally, where did this 1/2 come from? This 1/2 came from the fact that we multiplied, in our very first step, we multiplied the first row by 1. So we don't actually have to do everything here on the right. This is just kind of what's going on behind the scenes. Behind the little curtain, you're multiplying everything by an elementary matrix. But if all we're concerned about is computing the determinant, we just have to keep track of exactly what our row operations are. And when we're done, when we get to the identity right here, what we can do is we can look back and say, when did we scale rows? And just look at the factor that we scaled by and multiply those up. So in this case, we have a 1/2 and a -1/6. So altogether, we can automatically know that our determinant of A inverse is going to be equal to 1/2 times -1/6. Just by looking, without looking what's on the right, without even touching the elementary matrices, all we have to do is take when we scale the rows and multiply those together, and that gets the determinant of the inverse. So the determinant of A is just 1 over that. In fact, if you want, you can actually just keep track of those instead. You don't have to invert it at the end. You can say, what did I divide by at each step? And multiply by those numbers. So we can easily get this determinant without necessarily doing the explicit pattern formula or writing down elementary matrices. All we have to do is keep track of what the row operations are. Another thing I want to point out, which I think is kind of good, is that you can, how to write a matrix in terms of its elementary matrices. So here we have A inverse is this. Well, so A, this means that A, which is equal to A inverse is equal to all of these matrices inverted. And that's going to be equal to the inverse of each of them individually. So we can take each of these individually and invert them, but they're going to be in reverse order now. Keep in mind, when you take an inverse of a product, you're allowed to distribute the inverse as long as you invert them. And this is going to showcase another nice property of elementary matrices. Is that they have very nice inverses. So for example, this first matrix right here, the inverse of scaling a row by 1/2 is simply scaling that same row back by a factor of 2. Similarly, the inverse of this next one, this row operation here corresponds to subtracting 4 times the first row from the second row. Well, to undo that, we're just going to add it back in. So the inverse of this elementary matrix is just going to be, instead of -4, it's just going to be +4. And we can keep going down the line. So now we have that -1/6. To undo a scaling of -1/6 in the second row, we just multiply by 6. -6, rather. But everything else is equal. And then finally, for this last matrix, to undo this operation of subtracting twice the second row from the first row, we're going to add that back in. So the corresponding matrix is going to be that. So it turns out that A, once you have your row operations done, once you've row reduced the matrix to the identity, there's a very easy way of writing a matrix in terms of its elementary matrices. All right, let's just do one very quick 3x3 example so we can see everything in action. So let's compute the determinant of this matrix. So we're going to compute the determinant of this one. And we're going to showcase exactly how easy this is. So when I went through it the first time, we went through it in detail so you can kind of see the theory and the understanding about why we can do what we're about to do. But now we're just going to do it. We're going to do it in this nice, easy example. We're going to calculate the determinant of this using row operations. So all we need to do, we could use the diagonal formula, which would probably be easier for a 3x3, but the goal is to extend this to higher. So once you know how to find the determinant when you row reduce, by row reducing, you'll be able to do that for any size matrix, not just 2x2s and not just 3x3s. All right, so what we're going to do is we're going to row reduce and keep track. All right, so the row reduction, we're just going to row reduce this matrix. So we're going to scale that. That one's already done. And it turns out this example is going to be very nice because those are already there. So we can actually move on to the next one, but we have a problem is that this one is not what we wanted. We're gonna have to swap a row. So the first thing we're gonna actually have to do is to row reduce this matrix is we're going to swap rows 2 and 3. And now we have to scale that row by a factor of 2. We also have to get rid of that 1. And finally, we would normally need to scale that one. That one's already done, but we need to get rid of this 3. And when we're done with that, we get the row, we have the identity. All right, so we now know a lot of things. So going from the beginning of why we care about this, I know that this matrix is invertible because we reduced it to the identity. These columns, these original columns that we have are independent. This matrix is invertible. And we also know that when we get the determinant, we know it's going to be not 0. All right, so how do we use this information to actually figure out what the determinant is? Right, so what we're going to do is we can think about it as just every time we divided a row, we're going to multiply by that amount. Right, so here in particular, we scaled by 1/2. So this is going to contribute a times 2 to the determinant of A. And every time we swap a row, so you scaling a row is going to contribute whatever 1 over that amount is. Whenever you swap a row, that's going to contribute a -1. And whenever we add, that's not going to do anything special. All right, so the only things we're concerned about is when you scale and when you swap. So we swapped in the first step, that's going to contribute a -1, a factor of -1. And then we also scaled right here. So that's going to we scaled by 1/2. So that's going to contribute a factor of 2 to the determinant. And these last steps right here, these are just adding rows to other rows. So those are only going to contribute once. And now we can just multiply these up. So we have 1 times -2 times -1. So overall, the determinant should be just -2. 1 times 1 times -2 times 2. And then finally, we had that very first swap in the beginning, which was -1. And altogether, we got -2. All right, so the determinant of A, so that might look like a lot of work, but if you're going to row reduce it anyways, you might as well be able to get the determinant out of it exactly, not just know if it's 0 or not 0. And let's just check this answer with what we know, right? So if we used our nice formula that we know, let's check this answer. I'm going to use the method where we rewrite the first 2 rows and just look at the diagonals. Right, so we have these positive diagonals right here. So those positive diagonals are going to give us 0 plus 0 plus 0. And we have these negative diagonals. So that's going to give us 0 or -0, -2, and -0. And sure enough, we get the same answer we do when we use row reduction than when we use the diagonal formula. So that shows that these are consistent. So what's really nice about this is there's nothing special about 3x3s. We can now go up to any number, and as long as we keep careful track of our row reduction operations, we can calculate the determinant of the matrix.